Good morning, everyone. So it's my great pleasure to welcome you to Tuesday's keynote. So I'm very pleased to introduce Abhishek Bhattacharjee, who's an associate professor of computer science at Yale University. His work on hardware optimizations for memory translation has influenced the design of TLBs and AMD CPUs and NVIDIA GPUs. His work on software optimization for memory translation has been shipped in the Linux kernel since version 4.14. And more recently, he's been building brain-computer interfaces, which will be the subject of today's talk. So please join me in welcoming Abhishek.
So just checking, am I audible at the back? We're good? Okay. All right, thank you, Natalie, for that intro. I'd like to begin by thanking Natalie, Tor, and Mike for putting this conference together. This is an enormous amount of work, so as a community, we really owe them a debt of gratitude. I'd also like to thank them personally for giving me this chance to speak to you at what is my favorite conference. So over the next hour, I'm going to be trying to tell you why I believe that the future of computing lies in its direct interfacing with the human brain. 8 years ago, I lost someone I loved very much to suicide. It was a profound loss for me. This person had brought me up and has shaped who I am today. I work on direct mind-machine teaming because I believe that one day it'll be able to help us heal the chronic pain and the acute anxiety that underlies a drastic step like that. I believe that one day these machines and this direct kind of communication with computer systems can help us heal the injured and the distressed brain, can help us protect it. And if we can do these things, I think we'll be able to augment other aspects of our cognition and decision-making. So I'm giving this talk today because I want to work with you to enable this future in a manner that's effective, safe, and ethical. So those are the topics I'll be going over today. So let me begin by telling you why mind-machine teaming is more intimately connected to the computer sciences than we may sometimes realize. In 1945, in The Atlantic magazine, an article entitled As We May Think was published. The author of the article was Vannevar Bush. Bush was a scientist, an inventor, and an administrator during World War II. In fact, his work paved the path to the Manhattan Project and the National Science Foundation. In As We May Think, Bush introduced what he called the MEMX, which was this hypothetical electromechanical system that I'm showing you a picture of. This is a picture from the original article. So the idea behind the MEMX is that individuals could compress and store all of their collections, their records, and their correspondence and books on such a machine, and then retrieve it fast and in a flexible way. And so the idea was that with a MEMX like this, it inspired the imagination to go after things like early hypertext systems, the World Wide Web, and knowledge-based software. But it also inspired a parallel set of questions at that time. What if we could connect the biological neurons in our brain with a machine like the MEMX? Could we then upload our thoughts, our skills, and our memories to such a machine? Could we download those things from such a machine? And if we could do these things, what else could we augment about human cognition? So this was the question that Vivian Dovey and William Gray Walter, set out to answer in 1964. They embedded electrodes surgically in the brain of an individual that they were working with. And they showed that signals picked up from the brain could be used to directly move across slides that were projected by a 35mm slide projector at that time. And this was the design of the first BCI, or brain-computer interface. Brain-computer interfaces are the underlying technology that will help us realize direct mind-machine teaming. Now, in the decades since that experiment, we've come actually a long way in showing what we can do by lifting brain signals directly and using it to move assistive devices and such. In fact, we've gone even further and started to modulate aspects of what makes us human, like our memory, in a manner that is reminiscent of the MEMX. For example, scientists have shown that there's an area of the brain called the entorhinal cortex. That's the part that I'm showing you highlighted here. When you electrically stimulate this area, you can arrest memory decline in individuals with Alzheimer's disease and dementia. And this is now a repeated experiment that's been shown to work out. And this is a big step because we're starting to see that there are ways of modulating the way our memories work using electrical engagement. Now, I'm not trying to say that we are on the cusp of building A, a MEMX, and then B, interfacing that with the brain. We're a long way from that reality. But I think we're at a point where there's been enough proof of concept experiments to get us thinking as a community about how we may be able to contribute to getting to that eventual vision. And I think there are two compelling avenues that we can take to achieve that. The first is that there is a real need to build computationally capable BCIs that can help us perform the kind of experiments that we need to do to help understand the brain better. So going back to this experiment with the entorhinal cortex, one of the reasons that this was successful is that we had BCIs, we'd finally built BCIs around that time that could handle the entire volume of neural data needed to actually experiment in this manner. I think that there's also another path to building computationally capable BCIs that can have immediate impact on individuals around us today. There are many already existing compelling use cases for using BCIs to help heal the injured brain. So let me walk you through a few examples. Let's take epilepsy. There's 100 million people worldwide that suffer from epilepsy. Depending on the region of the world that you're in, about a quarter to half of those individuals suffer from seizures that last tens of minutes per day to hours per day, despite using pharmacological drugs. For these individuals, the FDA already approves the implantation of devices under the brain, placed in brain tissue, where electrical stimulation of certain spots in the brain can mitigate the rise and propagation of seizures. So there are several companies that do this today. There's thousands of individuals in the US itself, actually, who have these implantable BCIs. And these devices have been shown to cut off about 50 to 70% of seizures in individuals that have them. In fact, about tens of these individuals are fitted with implants every year by my collaborators at Yale. Another area where BCIs are showing incredible promise in clinical trials is in restoring movement to individuals who are paralyzed. So if you look at the video on the left, this is an individual who is completely paralyzed, but there's an implant in this person's brain that's picking up electrical activity associated with desired movement of the body. That electrical activity is relayed to assistive devices like that robotic arm that can reconstruct the movement that this individual has lost. If you look at the picture on the right, it's a similar use case. This is a recent experiment that was performed at Stanford a few months ago. An individual who had lost his ability to speak because of paralysis had his electrical signals corresponding to lip movement, tongue movement, and jaw movement interpreted by a BCI that could then reconstruct what this individual was trying to say and emit it on a terminal. Now, with this technology right now, we're emitting about 60 words per minute at about a 95% accuracy. In normal conversation, we speak at about 160 words per minute. So there's a long way to go, but it's a start. And that's the kind of start that we are seeing now in a whole host of other areas where implantable BCIs are already making a difference. So for example, Parkinson's disease, implantable BCIs are now an FDA-approved form of treatment for people that have drug-resistant Parkinson's disease. There's been clinical work showing the promise of BCIs in restoring vision to people with damaged photoreceptors. There's a whole host of these other experiments ongoing as well. And for this reason, the FDA is now investing quite heavily in this space. This is a bulk of text lifted from a guidance document on BCIs that the FDA published in May 2021. And what it really highlights is their excitement at the promise that implantable BCI devices offer in benefiting people with severe disabilities. As a consequence, the FDA has now created what they call their Breakthrough Medical Devices Program to accelerate the testing of these devices and the clinical approval process. And companies have taken note. So this is a non-exhaustive list of startups that are now working on neurotechnologies. They're working on everything from the BCI platform to safe surgical embedding of the BCI using even microsurgical techniques that do not require open brain surgery. In 2021, they raised about $530 million in venture funding, but this just scratches the surface because market studies are showing that just even implants for people that are paralyzed might be a $20 billion market. So there's a lot of headroom here to explore. Now, I started this talk by telling you about my personal loss and how it's driving my sort of interest and passion for this work. BCIs are increasingly showing a compelling line of treatment to handle chronic pain and alleviate suffering, anxiety, and depression Now, we're at the initial stages of using BCIs to do this. There's a long way to go, but there are examples of real people that have been implanted with these devices that are benefiting from them. And I think this is a topic that would impact almost everyone in this room if you look at the sheer number of people that suffer from mental illness, addiction, chronic pain, and neurological illness. These are just numbers collected from the US. And if you total these up, you're looking at anywhere in the range of about 1 out of every 3 to 1 out of every 4 people in the US impacted by this somehow. These numbers are worse when you consider the worldwide numbers. So to recap, what I hope I've done so far is help you understand why I think that BCIs will help us learn about the brain and will help us heal the brain. And in the long run, I think we will be able to use BCIs to help augment the healthy brain as well. So now, for this audience, I think the interesting question that we should be asking is, we're computer systems practitioners. What can we do to help advance this field? So this is a question that I started asking myself in 2016. This was about a year on from my loss. And the hunch that I had was that if you think of BCIs, it's really like a new form of input-output to your computer systems. And the fact is that whenever we have had innovation in new I/O, we have required innovations in computer systems design to take advantage of that I/O. I think that a great example of this is Sketchpad. So Sketchpad was a computer program made in 1963 by Ivan Sutherland. It was the first computer program that allowed humans and machines to converse via the medium of line drawings using a stylus and a touchscreen. We take these technologies for granted today, but they were revolutionary back then. But the point is that there would be no Sketchpad had it not been for the rise of MIT's TX2 machine. The TX2 machine pioneered a whole host of computing innovations that we now just teach in our intro-level CS classes, which was at the heart of getting the computational horsepower needed to support Sketchpad. In fact, so successful was the TX2 that it was what gave rise to Digital Equipment Corporation, which is the ancestor to practically all the research that we're doing in this community today. And so the way that I like to think about it is the following. If the computing systems innovations in the TX2 were needed to support Sketchpad and its new forms of I/O, imagine what kinds of computer systems innovations we need in our BCIs to interface with the brain. So to learn more about what that picture might look like, I decided to spend my post-tenure sabbatical at the Princeton Neuroscience Institute. So over several months there, I learned the basics of brain anatomy. I learned how to do craniotomies on animals, and I learned how to record neural data from some of the deepest recesses in our brain. A lot of my work was done with organisms like mice, and this video that I'm showing you on the right is one that I collected in imaging an area of the hindbrain of a mouse called a cerebellum. The cerebellum is known to be associated with neuropsychiatric disorders, which is why I was interested in it. But its depth and the challenge of reading from signals there really gave me an understanding of the challenges that we would face in building systems for BCIs in general. So let me walk you through that now. Before I dive into that, I just want to tell you a little bit more about the BCI landscape, because I've been referring to BCIs as if they're all of the implantable kind, but that's not true. There are also non-invasive BCIs in the form of wearables and helmets, and they can read neural signals. The good news is they don't need surgery. The bad news is that the skull effectively muffles the electrical activity of the biological neurons in your brain. And so for the really cutting edge BCI algorithms that you need to treat disorders, neurological disorders and neuropsychiatric disorders, we really today need something implantable that gets you brain signals directly from the cortical surface of the brain. And implantation basically sets up a whole list of systems challenges that I think this community is well geared to address. So here's the first one. Brain tissue is incredibly sensitive to heat. Just increasing the temperature of the brain tissue by 1 degree Celsius or more risks damaging the cellular tissue. And so if you look at what the FDA and the IEEE sort of recommend, is that implants placed on the cortical surface of the brain not exceed about 15 milliwatts of power. Now, this is really hard to meet when you consider the sheer volume of data that you want to extract from the neurons to do something useful with BCIs. So in all of our brains, we have about 86 billion neurons. And if you do the math using the sampling rates that neuroscientists like to use to drive BCI applications, that's like reading tens of terabits per second of data. That's a lot of data. Now, you might not need to get all of it, but you do need to get somewhere within that striking distance to do something useful. And today's BCIs are woefully inadequate at getting that data under the power cap that we have in mind. So for example, state-of-the-art commercial BCIs drive at about kilobits per second before they blow over that 15 milliwatt power cap. Now, there are ways to get around this and drive the bandwidth up further, but you do that by compromising on other design goals that I'm going to be talking about shortly. Before I get there though, let me make one more point, which is that the rate limiting step in BCIs is not the sensors anymore. In fact, the quality of the sensors that we're building are getting so good that, not only is it the case that the number of sensors we can read from is exponentially increasing, but that rate of exponential increase is also going up. Historically, we could double the number of neurons we could concurrently read from roughly every 6 years. In the last 5 years, that has started now doubling every 2 years because of improvements in the microelectrode technology and the packaging technology. So the rate limiting step at this point is, what do you do with that data? Can you process that under the power cap that we have? So the goal of my group has been, okay, the tens of terabits per second seems like a really hard target to meet. What can we do to get us there? And so a lot of the hardware I'm going to be talking to you about is going to focus on decoding at tens of megabits per second as a starting point. Now, there's one more problem here. It's not just that you're trying to read this volume of data under that power cap. It's also that you're trying to process it within real-time latency constraints. So take a seizure, for example. If you want to effectively mitigate a seizure, you have to electrically stimulate the area that you think the seizure will propagate to within about 10 milliseconds of when the seizure was first detected. That's when you get optimal treatment. And so this real-time latency constraint is going to make it even harder to meet our performance goals under that power cap. Now, one way that commercial BCIs have tried to address this kind of conflicting set of issues is by specializing the hardware in a big way. But I'm going to submit to you that that's also a problem because we really want flexible hardware, not something over-specialized. And there's a few reasons why. The first is that study after study after study shows that if you want to effectively treat a disorder, you have to personalize the algorithmic protocol to the individual. If you overly specialize the hardware, it really curtails the effectiveness of the BCI. So you cannot build something overly fixed function. The second problem is that this is a nascent space. So the pool of algorithms we want to support is in rapid flux. There's many algorithms coming up the pike. If an individual is going to go through the surgical risk of embedding one of these devices in their brain, you better be able to support whatever cutting edge algorithm is coming up next. Okay, so there's another reason for flexibility. And finally, this is a point that I think this community will understand and appreciate. Building a flexible programming substrate allows a stable piece of hardware, and that in turn allows software developers to be unlocked from the low-level details of hardware design, and it promotes programming productivity. People can go off on their own, build their algorithmic tool chains and their software stacks without worrying about whether it's going to be supported by the underlying hardware substrate. So for all of these reasons, flexibility in programming is actually another goal. And finally, all of the goals that I've outlined, they apply not just to engaging with a single brain site, but also with additional brain sites. We really want multi-brain site interfacing. And the reason that we want this is that there is ample evidence that practically all neurological and neuropsychiatric disorders are what are known as network level disorders. So again, if you take a seizure, it can start in one brain location, but it more often than not migrates to other brain locations. So being able to read from multiple brain sites and electrically stimulate different sites gives you the best line of attack at treating these kinds of disorders. And so this is the span of design goals that we have to meet overall. And to recap, what I basically sort of explained to you is why I think decoding, healing, and augmenting the brain is in our grasp, but why, to get there, we're going to have to solve some really hard computational challenges. One way to think about everything I've just said is that you want a flexible hardware programming fabric that's pulling out data that's about 100K times higher than what a 4K video stream requires, all under 15 milliwatts. If you do the math, the kind of communication links that you need to support this are usually underwater submarine, like those cables that allow you to connect telecom between different continents. So this is a tall ask, right? So I'm going to next deep dive into the steps we have been taking in my group to try to address these problems. I'm going to start with our single site BCI that we have designed. It's called Halo. It was first published at ISCA 2020, and there's been a series of follow-up papers that outline things like our chip design. So we've done 2 runs of chip tape outs in a 12 nanometer technology that I'll talk about today. Once having discussed Halo, I'm then going to start addressing this multi-site interfacing question. So we have an upcoming ISCA paper that shows how you can design a distributed network of Halo chips placed on different brain sites to realize a distributed BCI that we call Scalo. So I'll be talking about that as well. Now, before I move on to that, I do want to spend a second saying that everything that I've just outlined is along the lines of performance and power. The reason for that is that that's my area of expertise. But I think it's really important to bear in mind that the safe use of these devices really requires engagement with experts in security and privacy, and understanding how those topics will help influence the ethics and the legal ramifications of what this technology will bring to bear. I'll talk to you more about this towards the end of this hour, but I do want to point this out now and say that I'm actively looking to engage with those of you who are experts here on these topics. All right, so let's start with Halo. And this is the set of constraints that I'm going to be targeting with Halo. So the best way to think of how we're going to go about designing Halo is to think about how a neural decoding pipeline looks. So neural decoding is the terminology used to indicate what happens when we pull out brain data and we process it to figure out what the brain's intent is. So at a really coarse approximation, there's 3 broad classes of processing that you need to do with brain data. The first is artifact removal. People who have implants in them tend to inject noise into the sensors by doing things that are completely innocuous, like moving their neck, snapping their jaw, sneezing, or anything like that. So the first stage is remove all that noise from the sensor. Once you've done that, you want to do some kind of feature generation and then some kind of feature classification. So this will allow you to figure out, for example, how some electrical activity in the brain corresponds to moving the thumb on your right hand or the big toe on your left foot, or something to that effect. Now, the actual algorithms that are used to realize those 3 core blocks, there's a massive array of them. And this is like a rapidly growing list. There's a whole bunch of signal processing and machine learning methods here. And I think in the long run, what will make the most sense is to distribute this computation over not just an implantable BCI, but some kind of external system. For example, I don't anticipate that training a neural network is ever going to really be necessary on the implant itself. You may want to do that in the external system. Maybe there'll be a need to do some kind of model serving on the implant though. So there's a lot of space here to kind of consider how we want to support things. But my group's focus has been on trying to figure out what compute is beneficial to support on the implant and how we do this under 15 milliwatts. So for me to tell you more, I now need to deep dive into what an implant actually looks like. And I'm going to use Neuralink's BCI as an example. Neuralink, you may have heard of it. This is Elon Musk's company, so it gets a lot of popular press. And it's reasonably well documented what the key components are. So let's walk through them. So the most important part of a BCI, you could argue, is the sensor. Without it, the BCI is useless. And there are many kinds of sensor technologies out there. A common one that is approved for use in patients by the FDA is the grid of electrodes I'm showing you on the bottom left, the Utah array. So this is a grid of about 100 silicon probes. They're about 4 millimeters squared in size, and they puncture the top 2 millimeters of the brain surface. Taken all together, they'll read the electrical activity of about 300 biological neurons or so. There are many other kinds of electrodes also that are approved by the FDA, things like grid electrodes, strip electrodes, neuropixels. These things give you different range of coverage of brain areas in depth. You can also, you penetrate into areas like the cerebellum that I talked to you about before, or the hippocampus with some of these implants. And finally, the one that gives you the maximal depth is something called the Spencer depth electrode, which was developed by my collaborator at Yale, Dennis Spencer. So it's one of those electrodes that we are familiar with in our group. So the sensors themselves are actually not a massive power hog. They're going to read data and occasionally electrically stimulate the brain, and they'll consume microwatts of power. Where power starts to go is in the digitization of those analog signals. So ADCs have a quadratic bump in power corresponding to the data rate that they're reading. For the data rates that we're targeting, which is in that tens of megabits per second, 46 megabits per second or so, that's going to take up about 2 milliwatts of power. The other big source for power is the communication link sitting on these devices. And this bears, this is an important topic, so it's worth spending a little time on. So we have gone with using radio links on our BCIs. Now you could say, let's use wires because wires will consume less power. And in fact, wires were often used in the first generations of BCIs. But the problem with wires is that they pose some severe immune responses from the brain. They carry a lot of risk of infection. And really, there's a move away from clinical deployment of wired BCIs. And so a radio link is what we want. But the problem with the radio link is that the radio consumes a lot of power depending on the transmission range that the radio has. So earlier in this talk, I'd shown you this speech to text BCI, and you'll notice that there is something mounted on the skull of this individual. The reason that there's this mount is that the radio link on the BCI has only short range transmission to conserve power. And that's why there's a receiver plugged in on that mount. Now, obviously, this tethers the individual. So we really don't want this either. And that's why in our design, we've been focused on using radios that can exfiltrate data in the range of tens of meters. But the penalty we're going to have to pay is that we will have to expend about 200 picojoules per bit to do this. So this is using a radio that has had FDA approval. That's what we are picking up off the shelf. Other factors that we had to consider included, for example, the antenna size on the radio. If that gets too big, that has form factor implications on the package as well. So these are all issues that need to be thought about. But what this leaves us with is for Halo, which is going to comprise the digital electronics piece of this, we have about 12 milliwatts to play with, give or take, depending on the algorithm that we're supporting. So that's what I'm now going to focus on. So these pictures are bare die shots of our second chip tape out in a 12 nanometer technology. I'm now going to tell you what's in this chip. And the centerpiece of this chip is a collection of flexible ASICs that realize the core signal processing and machine learning algorithms that I pointed out before. Now, they're ASICs because we need power efficiency, but we do need flexibility for all the reasons that I've outlined before. So to help explain what this flexible collection of ASICs look like, I'm going to show you what kinds of workloads we support. This is the 4 broad classes of workloads that we have. And the reason we picked these is that they sweep through all of the bigger sort of list of signal processing and machine learning kernels that I showed you before. They're not a one-to-one match. You can think of them as exemplars of those different approaches. So they tell us the likelihood of being able to support that kind of compute on the BCI under the power cap that we have in mind. So let me walk you through each of these in a little more detail now. Okay, so let's start with lossless compression. So here's the idea behind compression. If you want to reduce the amount of power being expended by the radio, you want to reduce the amount of data that the radio needs to send out. You can do this with compression, and this is worthwhile to do as long as the hardware for compression itself isn't consuming so much power that it's outweighing the benefits of this. And so we decided to study this by taking a range of off-the-shelf lossless compression algorithms based on Lempel-Ziv and discrete wavelet transforms. The compression ratios that these offer you are really dependent on what brain region you're pulling data out from. So we looked at brain data collected from the motor cortex strip of the brain. So this is a part of the brain that tells you how a user is trying to move parts of their body. And we picked up electrical signals from the arm region and leg region of a non-human primate. And we saw compression ratios of about a factor of about 2 to 4. And again, it varies a lot on the brain region you're targeting. What this buys us overall in our system is roughly a factor of 1.4 savings in power because of how much that cuts down what the radio needs to send out. Now, I want to stop here and sort of emphasize 2 things. The first is I made a big deal about the word lossless. So why? We use lossless because neuroscientists don't yet know enough about the brain to feel confident dropping data. Now, in the long run, personally, I think lossy compression is what we will use because even if you look at the sensors, I mean, they're not a perfect fidelity. There's noise being injected. They're losing some data as well. But this is the quickest path to real world adoption by neuroscientists today. And that's why we picked this practical path to start with. That's the first point. The second point is that there is one exception to everything I just said. There is one kind of lossy compression that neuroscientists are comfortable using, and that's because they use it as a first step to movement decoding pipelines that they already have, and that is spike detection. There are some workloads where neuroscientists are comfortable changing the analog waveform of the brain signal into a train of positions where spikes are seen. And this also is a form of lossy compression. On the data sets that we had, we found that about 30x is roughly the amount of data that you save using well-known spike detection techniques like nonlinear energy operators and discrete wavelet transforms. And so this is also what we are going to support in Halo. Now, next, this brings me to movement intent. So we support two kinds of movement intent in Halo. Now, these are, remember, the algorithms that allow you to figure out how a paralyzed individual is trying to move their body, for example. And the key here is that these are part of a closed loop. So you need to read the brain data and act on it within 10 milliseconds or so. So there's this real-time latency constraint that you have to meet. There's two types of decoding we support in Halo. The first is for essential tremor. So this is the involuntary movement that people who have, for example, Parkinson's disease suffer from. Normally, the FDA-approved implants that are used for Parkinson's disease are always on to electrically stimulate the brain to prevent essential tremor. But because we can detect when essential tremor actually happens and only then turn on the electrical stimulation, we save battery life on our device, and we also reduce the chance of side effects that the individual may encounter from excessive electrical stimulation. So that's one of the first points. The next thing that we support is hand and finger movement detection. And there's many approaches to doing this. We picked one that's a fairly mature neural pipeline using spectral processing and a linear classifier like a support vector machine. And I'm happy to talk to you offline about all the work that's shown that this has a decoding accuracy of anywhere in the range of 90–95% or so. So this brings me to the last set of workloads that we support, which have to do with seizure detection and treatment. And again, like movement intent, this needs to be done in real time. You have about 10 milliseconds between the start of a seizure and electrical stimulation to mitigate it. There's again a whole staggering array of workloads being developed in this space. But what our collaborators at Yale sort of recommend is an approach that subsumes the merits of many other algorithms for seizure detection and consists of spectral processing, bandpass filtering, cross-core similarity measures across brain signals, and linear classifiers like support vector machines. And in the studies that they've done, scientists have found that this is good at detecting about 90% of the seizures in the individuals that have these implants. There's lots of studies that sort of rate what that effectiveness is that I'm happy to talk to you about offline. So that concludes the 4 set of workloads that we're going to support. One thing that I should mention is that neuropsychiatric disorders are not showing up here, but they are absolutely impacted by these workloads because neuropsychiatric disorders are an emerging line of treatment that we are trying to vet out by first using the workloads that support seizure detection and movement intent. The same underlying kernels are often used for neuropsychiatric disorder treatment as well. So that's why these 4 workload classes are so pivotal to support. Now, in Halo, we're going to build hardware for this. There's a few design principles by which we built the hardware. It's easiest for me to show you what they are by showing you what the actual hardware looks like. What I want you to remember right now, though, is that you might think that we will need a separate ASIC for each of those 4 workload classes that I talked about before. But actually, what we have found is that a finer grained distribution of ASICs does better. So let me show you what I mean. Let's start by looking at the LZ4 compression algorithm. Now, you might build one ASIC for LZ4, but here's what we found. If you actually look at the compute within LZ4, you can break it down into 2 distinct computational phases. If you build a separate ASIC for each of these separate computational kernels, you can clock them at lower frequencies than you would have had to the monolithic ASIC, which is your baseline. And in this example here, that saves us roughly a factor of 5 in terms of power. Now, the other thing that we can do with this approach is we can start reusing pieces of hardware for different workloads. So consider LZ4, another compression algorithm. Instead of building hardware for the Lempel-Ziv step again, you can recycle the ASIC for the Lempel-Ziv, stick in a programmable switch between the Lempel-Ziv and the linear integer coding, and allow that programmable switch to route data flow to a separate MA stage. In fact, you can drive this even further because the MA stage can be split into a separate MA and a separate range coding stage. And that allows you to clock everything down to its minimum level of frequency to meet the 46 megabit per second data rate that we're lifting off the brain. And that means that we can reduce power from 22 milliwatts to roughly 7 milliwatts here. Now, there's 2 points I want to make. First of all, we were interested in rapid prototyping of the hardware. So when we did all this, we pushed our hardware into high-level synthesis flows. HLS flows already have baked in them circuit-level optimizations to drive power down using pipelining, precision tricks, and so on. You can probably drive this power down even more by using custom approaches to handle those things. We view those as a complementary toolbox of techniques that you'd want to use along with the architectural level insights that we have. to do this kernel decomposition. Okay, so going forward with this kernel decomposition, we were able to support other compression algorithms by reusing the MA and the RC stages. And we started supporting spike detection as well in the same way. With spike detection, we can reuse the DWT ASIC for one of those pipelines as well. Same story with movement intent. We need FFTs, support vector machines, and a thresholding function. But the nice thing is that some of those components can be shared with seizure treatment protocols as well. Now, some things to keep in mind, obviously, we will now need our ASICs to be somewhat parameterizable if we're doing this. Some of the workloads require, for example, your FFT to be configured with different points. So we need support for that. But assuming that you can provide all that, the power savings are quite immense. So these are the power and frequency numbers from a detailed 28 nanometer physical synthesis flow that we extracted. This is a busy slide. I don't need you to look at all of these numbers. I need you to focus on these. This is the power saving that you get using the Halo PE approach instead of the monolithic ASICs. Okay, so we use these 5 design principles to build up that Halo chip, but there's actually a 6th one that bears mentioning in a little more detail. And that is that we built these accelerators to really genuinely be distributed. Here's what I mean by that. Our accelerators are working in distinct clock domains. Normally, when you have accelerators, you tend to have them operating in clock domains that are multiples of some baseline frequency. Here, they're truly disjoint, which means that we need separate ring oscillators and possible clock generators per clock domain to support this. So we have synchronizers, which are a standard tool that you need to handle inter-clock domain crossings. We had to work with that. We also had to make sure that there's no data loss over here. So there are FIFOs sitting between sender and receiver PEs that buffer in data. There are some PEs that actually sprint out output tokens in a manner that's data dependent in the input. So take compression. It's going to generate output based on the input that it's being fed. So we had to size our FIFOs to buffer everything and not drop data. And this had to be done with a lot of care because if the FIFOs get too big, they end up consuming too much power. So the paper has a lot more details on this. I'm happy to talk to you about it offline. But at this point, I want to take a step back. So what have we done? In building Halo, we have built a collection of ASICs, right? That's where we're at. But the long-term vision of Halo isn't just to have a collection of ASICs. I think eventually what will be needed is the full run of hardware compute that spans the gamut of extreme programmability and extreme power efficiency. And the reason for this is that you need the collection of ASICs to get FDA approval to treat a disease. The FDA is quite strict about making sure that something like seizure treatment is going to happen in just the milliwatts that they think is tolerable. But if you can build a solution that shows that that support is in there, you then have headroom to put in things like vector processors and CGRAs and whatnot to support other more speculative algorithms. And that's why I'm also interested in providing that support. In fact, in our current Halo setup, we actually already do implement something more general purpose like a microcontroller already. We need microcontrollers for 2 things. 1, to configure the data flow switches that I'd shown you before, and 2, to help parameterize the PEs. And so that explains this picture on the left, which is a circuit diagram of the Halo chip. It's got that cloud of ASICs on the left side, the microcontrollers on the right side. Now, we are de-risking our design, so we haven't built out all the hardware in one shot. As I'm learning about chip design, it's an incredibly fraught and difficult process to do. So the parts that are in our Halo chip are the shaded PEs that I'm showing you, the black PEs, and in another couple of generations, we expect to have the other PEs in there. This is all in a 12 nanometer technology. Okay, so where are we now going with this? There are epilepsy experts at Yale that we're engaging with. We are starting to look into doing animal testing with the Halo chip with mice and then via surgical embedding in pigs as a next step. As part of these discussions, an interesting topic that has opened up is the possibility of packaging the BCI in new technologies. So there's startups out there that are cranial prosthetic startups that remove a portion of the skull and replace it with a fused, safe plastic or metal material on which electronics can be embedded. And so this may allow us to have more operating power headroom for some of Halo's designs, and that's something that we're starting to look at. And so to recap, with Halo, where are we at? Well, what I presented to you is a hardware substrate that operates under 15 milliwatts. For the workloads that need it, under 10 milliseconds is the real-time constraint that we meet. Although most commercial VCIs are specialized to support only one workload, we support at least 6, though we want to go higher. And we're supporting an interfacing rate of about 46 megabits per second. instead of tens of kilobits per second. Now, I think we can do a lot better with this than this. And I think that there are many topics that all of you are working on that can help improve this design immensely. So for example, all of the stuff that I told you about in terms of identifying the kernels that we want to build ASICs for was completely done manually by us. But there are many of you working on automated program synthesis or compiler-driven ways to do this. In fact, I think there's going to be a few papers on this topic here at ASPLOS. So I think the techniques that you're using would have immense value in taking Halo further. Building of CGRAs and vector processors, many of you are working on that. I think that's a ripe domain to improve the hardware as well. And then there's this question of machine learning. Increasingly, the BCI community is seeing the value of using neural networks to decode brain activity from electrical signals. I think there's a whole host of questions about what this ML support should look like. What should be on the implant? What should be off the implant? How would you reduce training time? These are all topics that we need to address. Finally, AR and VR. BCIs are actually quite intimately connected with that technology. So for example, seizures. It's well known that if you equip a BCI along with VR goggles that do eye tracking, you can much more effectively detect the onset of a seizure hours beforehand. And so that's the kind of collaborative technology that many of you are working on that could make a real difference here. So these are some of my favorite papers that some of you are working on in this space. This is a non-exhaustive list of those papers. They cover the span of topics I've just indicated, and I invite you to join this BCI community to improve on the hardware that is being built here. Some of you are already focused on that. So for example, there's excellent work coming out of Luca Carloni's group at Columbia, Josh San Miguel's group at Wisconsin, and Andreas Moshovos's group at Toronto working on these problems, building hardware to handle machine learning or other decoding methods, both on the implant and off the implant. And there's a long way to go as well. Okay, so let's recap. I've shown you why I think that decoding, healing, and augmenting the brain has profound implications on our society. I've talked to you about the computational challenges that we need to face to meet that goal, and I've presented Halo. So what I now want to do is to drive up one of these things that Halo provides even further, which is the bandwidth. Can we do better? Can we now interface with the brain at a higher data rate? And that is what we're going to do with Scalo, which is the distributed network of Halo chips placed on multiple brain sites. My goal is going to be to drive up that interfacing bandwidth by at least an order of magnitude. In addition, I'm going to show you that distributed BCIs are a more native match for the kinds of network level disorders that accompany neuropsychiatric and neurological problems. Let me show you what I mean. So here is an example of what we want to do with Scalo. We want multiple implants engaging with different brain sites. And the reason that this is beneficial is the following. Let's say that there's a Halo chip on one of these implants. It's detecting the onset of a seizure. What we really want to do at this point is probe the other implants, see what electrical activity they're seeing, and track down if there is a correlated seizure emerging in those regions, or whether the seizure from the starting point is going to end up traveling there. Because those are the seizures that we need to address. And if we can electrically stimulate where the seizure is going to go, we improve our treatment options dramatically. So what this allows you to do is two things. You're now figuring out exactly where you want to apply the electrical stimulation and exactly when. And it's really cutting down the need to over-apply electrical stimulation, which has a bunch of side effects, as I mentioned before. So this is what we want to do. But I should state that a distributed BCI is very much a thing of the future. With single point BCIs, there are commercial BCIs out there. The problematic aspect of those commercial BCIs is that they eschew on a flexibility or power or interfacing bandwidth. The problem with what I'm just showing you now is that there is no commercial distributed BCI at all. So I do want to emphasize that to get there, we have to do more than just handling the compute and communication, which is what I'm focused on. We also need to understand how to surgically embed multiple implants in different brain spots in a manner that's fair. There are people working on this already. We also need to reduce the form factor for the packaging. There are people working on this already as well. So what we can do is look at the compute and communication. So let me tell you about the challenges here. I made a big deal about the power cap. Now you might think that if I'm going to put multiple implants in different brain areas, I now need to reduce that 15 milliwatt cap because the implants may thermally couple with one another. So here's the good news. Your brain is suspended in something called cerebrospinal fluid, and that does a good job dissipating heat. It's so effective, in fact, that your heat goes down exponentially from the implant location site. So as long as your implants are placed about 20 millimeters apart, there's negligible thermal coupling. Theoretically, in an average adult healthy brain, you should be able to place 60 equidistant implants without a problem. As theoretical, you wouldn't really want to go do this, but theoretically it could be done. And so power is not really the issue. The issue, on the other hand, is communication. So here's the problem. When you do the seizure correlation analysis that I was alluding to before, you usually have to send information for 4 millisecond snapshots of electrical data from different brain regions. For the sensors we have, that's like sending 23 kilobytes of data for every 4 millisecond window. Now, the radios that are on board these implants that are safe to use for the transmission distance within the brain of about 20 centimeters or so, those operate at about 7 megabits per second for the bit error rates that we really need, which have to be very low so that you're not losing data. And that means that the latency to send all of this data, even for 2 implants, goes well over that 10 millisecond cap that I'd shown you before, and it's in the 25 millisecond range. If you put in more implants, this is going to get worse. So the point with Scalo is, how can we reduce this need for communication overload? And the way we do this is by leveraging the following insight. Technically, you don't actually need to transmit all the data. If you could find a way to transmit the data that is likeliest to indicate a correlated activity, that would be enough. And so we use locality-sensitive hashing to accomplish this. The basic idea is the following. Let's look at those 2 brain signals. You can see that they're correlated. They may be stretched out in time and warped in amplitude, but they are highly correlated. If you can design a hash that collides to the same value for each of these correlated kinds of activity with a high likelihood, then you can use that as a filtering step before all the communication needs to be relayed to figure out whether the full signal is worth actually relaying. So here's what I mean. This is going to save us about a couple of orders of magnitude in bandwidth. And here's how it's going to work. So suppose you have a source implant. What you want to do is sense the data and store it on some onboard storage that we now have. You want to generate these hashes. You want to detect seizures. As soon as a seizure is detected, you broadcast the hashes that you've been generating. Destination implants do a check between the hashes they're receiving and the hashes that they have. And only if there's a collision do they think, oh, now I think the signals might actually be correlated, so I better check. And so they'll send a signal back to the source to transmit the full amount of data and do an actual signal similarity step there and confirm that there's actually some kind of correlation at that point. Now, for this to work, the hashing has to be aligned with the similarity measures themselves. You need those hashes to collide when things are supposed to be similar. And so we studied a whole host of similarity measures well known in the neuroscience space. Here's 4 of them that we support in Scalo. They have different complexity of implementation costs and complexity of power costs. And there's a lot of details in our Scalo paper on how we accommodate them. But the main point is that you might think that we would need a separate ASIC for each of those hashes. But just the way we did in Halo, we found kernels within those hashes that were common, things like dot products, frequency binning, and so on. And we built separate hashes for them so that using a smaller pool of hash ASICs, we could realize all the hashes needed for our similarity metrics. Okay, I won't have time to go over it here, but there's a whole host of other things you need to do to make accelerators actually useful. I mean, this community knows better than most that an accelerator is useless if you don't have the right software and programming support for it. So our paper has lots of details on how we meet software abstractions to well-known languages in the signal processing world like Trill DSP and Extreme to actually program these systems. Happy to talk to you more about that offline. But to recap, what I've now shown you is how we meet the computational challenges that we set out, or at least take a path in that direction using our Halo and Scalo designs. Okay, so where are we going next? Part of the deployments of the BCIs that we're testing in pigs will actually involve Scalo. The size of the brain anatomy of a pig should give us enough headroom to start out with at least a couple of implants in our design. As part of this, one of the interesting things that's come up is that the Halo chips are small enough that we think we can pack them on the sensors themselves. And I think this may open up interesting opportunities for in-sensor compute and may help us transition some of the awesome analog computing work that's going on in this domain and put it close to the close to the sensor in some sense. I think, for example, neural decoding with machine learning, I mean, this may be an opportunity to use analog work in the ML space in new and interesting ways. The more general topic of machine learning, I think, is a really interesting one. for this community and for BCIs. It's one that I've only recently started to think about. Basically, as the number of implants we're building and the range of brain data we're pulling out is getting bigger and more versatile, we're finding that you can train neural networks and deep nets to infer really interesting things about what the brain's intent is. But the main problem with this is that training times are high. And this is a really big problem with BCIs because your brain has plasticity. So in that speech-to-text BCI that I talked about before, for example, you need to retrain the BCI to the patient every single day for at least a couple of hours for the BCI to have any decoding accuracy. So there's a real question here, I think, which is one that many of you are thinking about, which is how can we start training these neural networks with fewer training examples? How can we inject some of the ability to draw analogies between domains that a neural network might be good at to cut down that training overhead? And the brain is the ultimate engine that can do this, draw these fast analogies. And so that is an area that I'm looking into. And I think it complements a lot of the neuromorphic computing work that is already ongoing in this group, in this community. So neuromorphic computing to this day has mostly focused on emulating in silicon the activity of spiking biological neurons. But I think there's a whole lot more that we could be thinking about that complements this. For example, let's think about how the brain actually draws fast analogies and learns from less training data. The way that it does this is that it actually has two units of operation, the neocortex and the hippocampus. What the neocortex is good at is learning complex patterns and associations. It needs a lot of training data to do this, but once it has figured out these complex patterns, it can learn by analogy. Okay, and this is the real power of it. Now, while the neocortex is learning slowly, there is also this hippocampus, which is sort of like a one-shot memorization pool, and it allows you to learn fast. You can think of this as nothing but a trace cache, which we're familiar with from the microarchitecture world. So suppose you're used to reviewer B giving you a crummy review and you're fed up of reviewer B, and this cycle keeps going, and then you respond to reviewer B and maybe reviewer B responds favorably. That is the trace that's going to be learned in the hippocampus over and over again. And then at some point, you will start consolidating that back into the neocortex so that that more abstract association is learned. So here's what we're sort of going for. These HPUs that I'm showing you in the neocortex as those higher level abstraction learning engines. They're the things that learn by analogy. So we want to train those up. What will train those up is specialized processors in the neocortex that respond to the sensory cue that you're giving it. So those specialized processors are drawing associations and pooling them to realize these traces in the hippocampus. And once those traces are seen over and over again, the hippocampus essentially pages that entire trace out in a process called consolidation, which often happens while you're sleeping, actually, into the higher level dimensional processors. And that is when the more complex analogies start to get drawn. And this is what allows the brain to learn from less training data down the line. So one of the interesting things that this should kind of remind you of, circling back to the start of my talk, is that the hippocampus is nothing but an expanded, the MEMX is nothing but an expanded hippocampus. That is exactly what it is. And so I think when we start building hardware that more natively understands these brain processes, that will unlock the potential for a whole host of interesting BCI interactions that go beyond what we can do today. So very briefly, my group's been working on some of this sort of high-level cognitive modeling aspects of these complementary learning system theories, which is what I've just presented to you. This is the stuff that you may be familiar with from Daniel Kahneman's book on this topic as well. I'm happy to talk to you more about it offline and about the compiler toolchain that we've been building to accelerate cognitive modeling. Okay, so once I've focused a lot on the opportunities that BCIs open up, but I should also say that I'm quite concerned about the ethical considerations that these devices are going to bring up. I grew up in a family of diplomats. We lived all over the world growing up. Some of the countries I lived in were run by, by military juntas, so highly authoritarian states. I'm actually not allowed to share which country I'm going to be talking about, but one of the countries that I lived in, some of the teachers that we had there actually were very concerned about surveillance from the state and espionage and interrogation of political prisoners. In particular, one of my math teachers when I was 14 had been a student of William Gray Walter, the person who did the first BCI experiment I showed you about before. And he had been part of the espionage ring protesting the military junta that was there in that country. He was later imprisoned many years after I left this country. So if you think that surveillance is a thing that's far ahead, it's actually perhaps closer than we think. This is a picture of a classroom in China where a wearable BCI is being used to track the focus of of students. The startup that provided this BCI is based in Boston. Now, this is a nuanced issue because, on the one hand, it's, perhaps nice to know that the people you're speaking to are getting anything from what you're saying, which I wish I knew in a little more detail. The downside is you're collecting a lot of data and pooling it in a central server. And yeah, we may not be able to decode all that data just yet, but we might one day. So there is this mental privacy issue we need to think about. And for that reason, there's actually ongoing work by the Council of Europe, a national commission in Chile, and an inter-academic neuro rights initiative that's trying to chalk up the mental right issues that we need to confront as this technology widens its scope. So for example, what does it mean for our personal identity to have a device that can electrically stimulate our brain and start changing our neural circuits? We need to start thinking about this. Does that impact our notion of free will? Mental privacy is something I've just discussed. Then there are questions like, if this technology starts to augment the healthy brain, how do we ensure that everyone gets equal access to it? And how can we protect from algorithmic bias? And I think down the line, this will actually influence our legal scaffolding because all of our Western common law is essentially strengthened around this idea of actus reus and mensa re. And what these basically mean is that you are only criminally culpable of a crime if you took bodily action to create the crime, or your lack of bodily action allowed a crime to happen. With brain signals moving assistive devices directly, this gets a lot cloudier to sort of judge. And if we ever start to getting to the point where we can decode subconscious activity from deliberate intent, this question is going to become a lot cloudier. There are legal scholars and ethicists already working on this, but I think as a community, we should start engaging with them. So I'd like to round out my talk now by thanking the people who actually make this work possible. My PhD students Raghav and my PhD student Karthik and my postdoc Raghav are absolutely vital to all this work. They're amazing. They've driven this entire enterprise and they're ready to start BCI labs wherever they go. So please find them and talk to them at ASPLOS. My students Mohammed and Michael are also here and eager to talk to you about what they're up to in this space as well. There are other PhD students and undergraduates who've contributed to this work immensely, as have our neuroscience colleagues. So in closing, I began by telling you about how my loss has shaped my interest and my passion for direct mind-machine teaming. My science is an expression of that. Thank you for allowing me to share that science with you today. I'm grateful for your time. Thank you, and happy to take your questions now.
Thank you so much, Abhishek. If you could come to the microphones with your questions.